This is one of the most highly tuned machines in the world. It was born for one reason and one reason only: to race. And win.
In just a handful of seconds, an F1 car accelerates to the kinds of speeds at which a jet aircraft takes off. In fact, they're so fast that the engineers have to work hard to stop them taking off. And that kind of high performance calls for titanium, carbon fibre, all those other exotic modern materials. But it also requires some surprising engineering connections.
A revolution in artillery. A new design for a jet engine.
Any second now, it's about to snap.
Oh yeah, there it goes, there, look, look. That's ruined.
An ancient boat. Protective armour. And a blacksmith's forge.
Chaps, broke my sword.
An F1 car has just one purpose in life: to go as fast as possible around a circuit for roughly 300 kilometers on a Sunday. Everything you see is engineered to improve performance, to shave weight and milliseconds off a lap time. The materials, the engine, the shape.
Famously, their sophisticated aerodynamics keep it pinned to the road so well that it could drive through the Monte Carlo tunnel upside down. Well, theoretically. But the thing is, there's nothing superfluous on these machines. Nothing that isn't about making it faster, pinning it to the road, or stop quickly. That's why there's no room for luggage or a map.
The result, a thoroughbred machine that weighs about half as much as a small runabout. But it's still a car. It does the same things as ordinary cars, just a lot faster, a lot more expensively, and without the indicators. You might think that F1 cars would be built around monstrous engines, but the engines are smaller than those in many family cars, just 2.4 litres. The secret is precision, not brute force. And that precision is audible. It's the distinctive sound of components moving at speeds that would destroy an ordinary engine.
The beating heart of any car with an internal combustion engine, be it a family hack or an F1 car, is this. This is the piston in the cylinder. We've cut the cylinder away here so you can see what's happening. And it starts with an explosion from fuel up here. That's the internal combustion bit of an internal combustion engine. Those expanding gases push the piston down inside the cylinder. That does two things by rotating the shaft at the bottom. Firstly, it sends another piston up to the top ready for its explosion to continue the process. And that rotating shaft ultimately is what drives the car's wheels. You can increase the amount of power by increasing the number of these pistons in their cylinders and by increasing the RPM, the number of times a minute that the piston goes up and down and turns that shaft.
While F1 engines might share the same basic design as an ordinary engine, a piston going up and down inside a cylinder, the engine in your road car would literally explode if it reached even half the revs that an F1 car is capable of. The heat and pressure would be too much. This is how F1 designers engineer the solution. They get more out of each explosion up here, thanks to a huge leap forwards in artillery development. Internal combustion engines are like cannons. They both use an explosion at one end to drive something along a tube. Same process, very different effect. And to get the most out of your bang, you must reduce something called windage. Not good for a cannon or a finely tuned engine. To find out why, I've come to a typically sophisticated and glamorous F1 location with artillery expert Nick Hall.
So this then is the point at which F1 technology and military artillery history come together. What do we need to make it good?
It is important to have the fit between the projectile and the cylinder. And in the early history of artillery, because you couldn't bore a cylinder very accurately and you couldn't make an absolutely reliably spherical cannonball, there had to be a gap so that the cannonball wouldn't jam, and so you lost power through that gap.
A windage gap was a safety feature to ensure that a cannonball didn't get stuck in the barrel. But there was a price to pay.
So this is the gap between the projectile, the cannonball, or in this case, the piston, and the cannon itself, the gap around the outside.
Yeah, that is the windage.
Well, I've got two projectiles here, two pistons. Now, we've got one is smaller than the other. One is a little bit smaller, there's a bit of a gap. Do you reckon that's sufficient difference between the size on the projectiles to make a difference in how they perform in the cannon?
Yes, I do, because that gap expressed all the way around is allowing a lot of pressure to escape.
So just that tiny difference will make a difference in what we see when they're fired out the cannon.
Yeah.
So, first, the smaller of the two, with the slight gap. This should affect the performance of the cannon slightly, but will make it safer.
I've got the bigger one.
Which is probably just as well, as this is the first cannon I've built.
OK, well, let's load it up. So, just drop that in.
Yeah.
It's in, I'd say. Now, let's charge the cannon.
My finely machined cannon stores air up to a pressure of 5 bar, or 72 pounds per square inch, which, when released, will hopefully propel the projectile down our makeshift range.
Right, our cannon is charged.
Yeah.
I'll go on 0.
So I can run.
3, 2, 1, go. OK, if we're ready, in. 3, I've never fired a cannon. You fired lots.
Yeah.
I'll just do it quickly. 3, 2, 1.
Released by means of a high-tech lever and rope assembly, the pressure forces the piston along the cylinder and into the air.
Well, it works, didn't it?
That's very good, wasn't it?
Well, that's it. That's the smaller projectile. So what we must now do is go and mark
smoke.
the spot with my industrial golf flag. Look at it.
A very respectable 48 metres on our first attempt.
Right. Well, this isn't an exercise in demonstrating the effectiveness of my air cannon, but come on, it's pretty good.
It's not bad at
So
all,
that's
is
the
it?
slightly undersized projectile, piston, with a slight gap in it around the cylinder bore, which we call windage. This one is now a snugger fit. So if this were too big and you had to squeeze it in, it would waste energy in overcoming the friction to shove it out the barrel.
Yes, but we've got very fine machining here, haven't we?
Only the best. OK, so let's put... Now, that is a closer fit.
In fact, such a close fit, it may need just a little persuading. With our snugly fitting piston finally in place, the air pressure is built up to exactly the same 5 bar level as the previous attempt. There is no windage gap in this one, no safety gap on my homemade high-pressure cannon.
Right, the cannon is charged. We've persuaded the projectile into the barrel. I'm going to stand a bit further away now because I'm suddenly a bit more nervous.
No windage on this one.
No. If I go on 3, 2, 1,
Yeah.
go.
Yeah.
OK, if we're ready, 3, 2, 1. Whoa!
Pretty convincing.
Yeah, it even sounded more dramatic at this end, and that's clearly gone substantially further because of that tiny, tiny bit less of a gap around it.
That's right.
So exactly the same force fired it much further, and all because of a better fit.
3.
Well, we know it went further than the previous attempt of 48 metres, but by how much?
11, 12. So this got an extra 12 metres.
From 48. So
25% increased range from just that tiny, tiny extra bit that closed the gap.
Yeah, so you're not wasting that pressure and gaining range by better fit.
But I really could not see the difference between the two. Barely, you could just about feel it with your fingers.
Not much more than
and this one is a
thumbnail thickness.
25% more efficient, effectively. It's the same charge, same power.
Yeah.
So it's more efficient by cutting down on that windage.
Precision machining meant gunners didn't have to allow for windage, all thanks to one John Wilkinson, known in his day as Iron Mad Wilkinson. In the late 18th century, he developed the cannon lathe to machine cannon barrels very accurately. And Wilkinson also realized his cannon lathe could make more powerful steam engines with precisely bored cylinders. The same principle makes F1 cars faster down the straights.
So just that tiny difference, that tiny increase in size, made all the difference in this as a projectile out of my cannon. And if we think if that were working as a piston in an engine, firing thousands of times a minute, it would make all the difference there as well.
F1 engines are so finely tuned and the fit between the piston and cylinder is so tight that you can't even start the engine when cold without damaging it, as Mike Gascoigne, an F1 technical director, explains.
So this engine right now is stone cold.
Yep.
And therefore, inside those cylinders, the pistons are actually
Too tight. If you
well,
start
pretty much
this,
attached.
yeah, if you start this now, it won't break, but it will wear and reduce its efficiency. So we have to plug in oil and water heaters, and we actually have them on timers overnight, such that they come on about 3 hours before we get in, such that the engines are sitting there at operating temperature, and then we can turn them over.
So when you talk about tolerances, which is how closely things are engineered and made in terms of size, in this instance then, they're so tight that until they're at the right temperature...
Yeah, they're hot home. They're actually fitted together when they're hot. So at the temperature they're going to be operating at, that's how they fit them together.
And this is why these things end up sitting there looking there like they're on life support.
Yep.
With warm water being fed to them and warmed oil to get them to operating temperature.
Exactly.
An F1 car revs to 18,000 RPM, 3 times what a normal car manages. An average car produces about 200 horsepower. An F1 car belts out 800. Mind you, it only gets 4 miles to the gallon. Its power translates into staggering straight-line speed, and that is a problem. A jumbo jet takes off at 290 kilometers an hour. An F1 car can exceed that speed 200 times during a race. Sometimes fast cars behave like planes. Manfred Winkelhock was lucky to walk away from this famous crash in Germany in 1980. It's all to do with the aerodynamic shape of the car. Get it wrong and it takes off. Get it right and you win races.
Thanks to an ancient, much slower and much quieter vehicle, the sailing boat, Formula One cars can keep all 4 wheels on the ground. The same principle that allows mariners to sail into the wind allows F1 cars to pin the wheels to the tarmac and corner faster.
Sailing in the direction the wind is blowing is relatively easy. Hold up a sail and you'll be blown along. Sailing into the wind is more difficult. More than 2,000 years ago, Arabian sailors mastered the trick by changing the shape of their sails. A triangular sail was the solution because it's a kind of wing, as aerodynamicist Phil Rubini explains.
Phil, I'm kind of familiar with the concept of a wing, that it generates lift. But how is a sail in any way like a wing? They're completely different, aren't they?
Well, they look different, yes, but if you think about a wing, you know that a wing will fly on an aeroplane. And so to keep this wing in the air, we need a force pushing up. And that force is generated from the air when it flies over the wing.
The aerofoil shape creates low pressure above the wing, and it rises. The same principle helps sailors, ancient and modern.
The Arabian sailors 2,000 years ago effectively invented the wing that we're using nowadays on aeroplanes. Now think of a sailing boat. The sail now looks a little bit like a wing, and as the sailing boat sails through the water, the air flows over the wing.
Like a wing, a sail creates an area of low pressure, and the boat wants to move towards it, effectively sideways. Add a flat keel, and the boat won't go sideways, but forwards into the wind. And that sail shape helps F1 engineers. This is not an F1 car, but thanks to a few modifications inspired by Arabian sailors, here in one of the world's most sophisticated wind tunnels, we can make it behave like one. Fast cars use aerodynamics to press themselves down to make themselves seem heavier. That doesn't sound ideal, but a heavy car is less likely to take off. In this tunnel, they have sensors to weigh the car. It's about a ton now, but that should change when we unleash the small hurricane they keep here. The wind pressing down on the upside-down wings creates downforce.
You can see there that's the downforce that is being produced. It's a minus number because the wings are pushing the car down rather than pushing the car up.
So it's minus lift.
It's minus lift, it's pulling it down, that's right.
My aero modifications press the car into the ground, good for giving the tyres more grip and good for getting round corners. The wind blows at around 130 kilometers an hour, but engineers here can calculate what its effect would be at 320 kilometers an hour.
So this screen is showing the same figures if the car were running at Formula One speeds. And at those speeds, it's telling us we've now got minus 1,195. So that's pushing down rather than lifting up. So that's some downforce.
My wings would make the car a ton heavier. It wouldn't take off.
It's a significant downforce now, but look at that drag figure.
It's enormous.
The huge wings create huge drag, or air resistance, which would slow the car. And F1 engineers struggle to reduce drag whilst increasing downforce. My car probably wouldn't even reach 100 kilometers an hour, unless I managed to fit several Formula One engines in there. It's an idea, it's not practical.
Well, a couple of things prove there, I think. Firstly, that I'm probably not going to be employed as an aerodynamicist on an F1 team anytime soon, but the theory does work. These spoilers, these upside-down wings, have the effect of pushing the car down and making it weigh, well, almost twice as much as it weighs normally. Thought occurs, though, because they really are just that, upside-down wings, pushing it down onto the road. All you'd have to do is turn them the other way up, and they're ordinary wings. They'd make lift. And it's not often you get a full-size wind tunnel to play with. So, guys, do us a favour. Turn them over. Gotta give it a go.
Now, let's see how light we can make this car.
So this is now actual lift we're looking
That's
at,
right,
rather than...
that's a positive number now, so that's showing that we've got positive lift, lifting the car up.
If my car were travelling at 300 kilometers an hour, it would weigh a paltry 200 kilograms, less than a quarter of its real weight. So in case you were in any doubt, aerodynamics make a huge difference to how any car behaves. But you wouldn't need to tell that to Manfred. To achieve the sophisticated aerodynamics of an F1 car, you don't simply bolt on a few spoilers. Every single surface of the car is profiled to produce the sweetest combination of maximum downforce and minimum drag. The right answers are the difference between just finishing and winning. According to most F1 engineers, Mike Gascoigne included.
So, my aerodynamics, we all know instinctively, you think, well, make something pointy and it cuts through the air rather than like a barn door pushing it out of the way, and that's kind of it, isn't it? I mean...
Well, no, because if you want to go in a straight line and go very quickly, that's what you do. You make it very pointy, very sleek, so you have minimum drag. But unfortunately, those cars won't go around a corner. If you want to go around a corner, you want to push down on the tyres, because the more you push down on the tyre, the more grip you'll get and the more quicker you'll be able to go around the corner. The classic thing, if you look at the grid in a Formula One race, and if you look at the car on pole and you're 2 seconds slower, 1.9 of that is aerodynamics, always.
An F1 engineer's brief is pretty simple. Shave seconds off a lap time. Usually the answer is also simple. Boost power or shed weight. But there is another way, through driver psychology.
Making a car faster means thinking the unthinkable about what happens when things go sideways, literally, because a safe, confident driver is a faster driver.
And thanks to a jet engine, F1 cars protect their precious cargo very well. Race cars, by their very nature, go very fast. And if something goes wrong, it goes wrong very fast. Amazingly, this driver also survived, because safety is now so important in motorsport. Formula One engineers have to tread the fine line between making their cars light enough to be competitive, but strong enough to be safe. This calls for material that is stiff, light and strong. A stiff, rigid car corners faster. It doesn't twist, so the wheels never leave the ground. A light car accelerates and brakes more quickly. And a strong car protects the driver. A nervous driver won't push the car to its limits. Finding stiff, strong, light material would be the holy grail for F1 engineers. 40 years ago, the aerospace wing of Rolls-Royce went out to do just that. They started work with a revolutionary new material. They used it for high-speed fan blades in their new jet engine. These had to be very light and very strong. Remind you of anything?
Just like aviation engineers, Formula One car designers are always on the lookout for lighter, stronger materials. And the answer to their quest lies beyond these doors. Only it's quite special stuff, hence the need to cover up. Perhaps not surprisingly, it doesn't exactly look or sound like an industrial revolution factory in here. It's all rather clean and neat and quiet. But what they're making is capable of putting up with some pretty rough treatment. So this is carbon fibre in its raw, floppy state. And you really wouldn't think that was much use for making jet engine fans or Formula One cars, for that matter. And you'd be right, in this condition.
It needs 2 extra elements before it's ready for the track: heat and pressure. Basically, you stick it in a big pressure cooker. A really big pressure cooker.
That is quite an oven door. Okay, so select gas mark 6 and, wait.
The material that emerges is lightweight, but incredibly tough. Tough enough to make an F1 car. All carbon fibre starts its life as string. It can be woven into cloth or made straight into a high-stress component. These carbon fibre drive shafts are destined for very expensive road cars and Le Mans race cars. Manufacturers and racers need to know exactly how much stress a carbon fibre drive shaft can take. And this is the world of Chris Jones, a test engineer for a leading manufacturer.
So, Chris, test engineer. I'm guessing that means you get to test things to destruction.
Yeah, pretty much.
Because that's where I think you can help me. Because I know carbon fibre is used in Formula One because it's light and because it's strong.
Yeah.
But how light and strong compared to other materials? And that's where you can help.
Well, what we've got here, we've got two prop shafts here.
Right.
I don't know if you want to pick that up. And,
so this is a steel prop
this
shaft.
is, yes.
So this big lump of metal connects the engine to the wheels.
That's
so
right,
all the
yes.
power goes through this.
Along the car, yeah.
Right,
That's right.
OK.
And here we've got the carbon fibre equivalent to the same thing. So if you want to pick that up and...
Doesn't weigh anything at all. But, I mean, obviously, if carbon fibre is as strong, if this is as strong as the steel one, it's a no-brainer because this is so much lighter, you'd use this.
Exactly.
But can you tell me how much so? Can you show me how much, if this is as strong as that?
I think we can do that.
What I'm asking is, can we break them?
Yeah, we can give it a shot anyway.
OK, right.
This rig uses torque or twisting force to test materials until they break. Sensors can judge exactly how much force it managed to cope with before snapping.
So when this is working at full tilt and at full power, how much torque can go through it?
So 8,000 newton meters we can put through with this rig.
It's really not the kind of device to catch a tie-in, is it?
No, not at all.
To put this in perspective, it requires around 2 Newton meters of torque to drive a corkscrew into a wine cork. This rig can produce 8,000. It's a lot of plonk.
So that piece of plastic and these glasses will protect us from the immense forces being unleashed with it.
That's the plan anyway.
Good. OK,
so,
fine. Yes. A bit further back, maybe?
OK, you should be OK there.
All
so, right. OK, well, that's on its way up. You see the numbers are rising here.
293. That's a lot of Newton meters of torque.
It is.
This is twisting.
You can see if you look at
torque.
this end here, you can see this end of the machine. It'll be twisting around. It's yielding already. Look. There we go.
So what's this showing us?
That's yield there. So the machine is about to fail. So any second now, it's about to snap.
Really?
So this the machine is just distorting now. You should be able to see it necking.
Necking. Yeah, I know what you're thinking, but here it means when a material gets thinner in cross-section. It's an indication it's just about to fail.
Oh, yeah, there it goes there. Look, look. Oh, it's gone.
I think we'll stop that there.
That's ruined.
I think it is.
You have broken that. What did it make it to?
That got to 1,376 newton meters.
1,300 Newton meters, and it's, well, it's now a corkscrew.
It is.
Yeah,
there you go then.
It certainly didn't spring back either,
No.
did it? That is quite badly spoiled. Well, now we know the limits for that one. Let's see what the carbon fibre equivalent can take.
OK, should we get that one in?
And straight away, that's a reminder of how much lighter this thing is.
Lighter, but in theory, much stronger. And much more expensive. £2,500 for this shaft alone.
It certainly looks better, doesn't it?
It does. Quite attractive, aren't they?
I can't believe it's going to have any strength compared with the big steel one.
OK, should we see what we can do out of this one?
Right. So 1,376 is the target. If it can match that, it's matched the much heavier steel.
Yes, that's right.
Pile it on.
We're off.
So it's climbing 647, 8. It doesn't hang about this machine, does it? 9, 10, 11. And we're getting close to where the steel went. 13. It's just gone straight past it. And it's
So there's no-
completely blitzed.
There's
it.
no damage to the shaft there whatsoever.
So this much lighter,
Much
prop
lighter,
shaft
much
is
stronger.
just gone completely howling past. What'll it make it to, do you think?
I'm hoping 4.5.
4.5
4.5.
compared to 1,300 for the steel, and it weighs so much less. Oh, we're on the way to that. 4, 2, 3, 4,
Oh, we're past.
5. Oh, was just about to ask what happens when it goes.
That's what happens
Now
when it
I know.
goes.
I didn't jump. I didn't jump. So it made it to...
It made it to 4,728 newton meters compared to our
1,300.
1,300-ish.
And it's so much stronger than the big heavy steel one. And let's not forget, it's just made of this stuff, isn't it? It's just threads. Basically, it's just
Expensive reel of string.
expensive string, isn't it?
Pretty
That's
much.
it. Just that.
Thanks to a jet engine, strong carbon fibre is perfect for making light, which means, of course, fast cars. You make an F1 car the same way you make a dress, by following a pattern. Every shape necessary for making all the component parts is precisely cut from carbon cloth, including this, the monocoque or single shell. It's the cockpit for the driver. This ultralight shell is also the body of the car itself. There is no internal frame. There's no need, because the carbon fibre is tough enough on its own. All that shields the driver is a skin of carbon.
But that's not the only thing that needs careful protection on these sleek beasts.
F1 cars run on pretty much the same fuel you and I get at the pumps. But petrol is petrol, and it's highly flammable. That's the point of this stuff. In races, F1 cars must now carry all their fuel from the start. 200 litres of petrol, travelling at 320 kilometres an hour. That is quite a missile. The tank has to be tough, or the driver could be toast. Strength usually has a weight penalty, but in the anorexic world of F1, that isn't an option. And thanks to a bulletproof vest, the cars stay safe, light, and fast.
For their solution, the F1 designers took a bit of a swerve. Rather than build strong, rigid fuel tanks to withstand impacts, they used something that works on principles closer to the way a car's suspension works. A bit of give. Down here I have a water bottle and a rubber gym ball, both with water in them. I'm going to drop them both off here, same height, 15 metres, and then, well, we'll see the principle in action. The bottle first, I think. So it's just up and over the edge, really. Here we go. Oh, dear. That didn't work. That would be bad in a fuel tank. And now the ball. Right.
That's more like it. Now, while our 15-metre drop may not have created F1-type speeds, it does a fairly good job of replicating the type of forces a fuel tank might experience during an impact. A lightweight, flexible material that bends and absorbs impact sounds ideal. Apparently, it's tricky to make something flexible and strong. Professor Paul Hogg is a materials expert from Manchester University.
Paul, all I've really demonstrated there then is, well, the solution. Why don't they just make Formula One tanks out of rubber?
OK, so it's nice, it's conformable, it'll put up with that sort of drop loading.
Yeah.
But what happens if you've got something sharp that's going to puncture it? This material is actually quite weak. Most of the things that make materials flexible tend to make them weak at the same time. So if you've got something sharp that's going to puncture that, you've got a problem.
OK, so if it's a sharp, pointy impact, something like, let's say, an arrow.
An arrow?
Glad you said that. Good, because over here, Master Archer Steve Ralphs is going to fire a flaming arrow into this, which is going to be, for the purposes of this demonstration, our fuel tank. It's another rubber ball full of fuel. I should put it on the target, like so. Steve?
And because our rubber ball has several litres of petrol in it, and we're about to shoot it with a flaming arrow, we thought it best if we had the local fire brigade sort of on standby. They have a lot of flaming arrow-related fires in Lancashire, apparently.
Steve, you reckon you can put a flaming arrow in there from about here?
We can but try.
OK. If you watch Formula One, you'll know this is exactly the kind of thing that can happen in a racing situation. We are flaming. Yeah. And that is why they banned crossbows at racetracks.
Whilst flaming arrows aren't usually an issue during a race, the 230-litre fuel tank in an F1 car sits in between a white-hot engine and a vulnerable driver. Any spillage, and you can have a fireball.
Possibly overkill there. That didn't work at all, did it?
Didn't, no.
Clearly, the rubber's just not... It's flexible.
Flexible, but it's just not strong enough, particularly when you've got that point loading on.
Which could well happen in an accident
could.
at a race. Not an arrow, obviously, but a piece of metal could go in. So how are we going to make something that is flexible enough and strong enough?
Well, we've got a bit of a problem there. I mean, we know that things that make materials flexible tend to make them weak, and it's the other way around. If you want to make something very strong, it becomes very rigid. But we've got a trick we can use in materials, and we use this a lot, and that's by making things very thin. And if we make a very strong material into a fibre, it's very thin and it becomes very flexible. This is Kevlar. It's a very strong material. It's actually a very stiff material, but in a fibre form, you can see it's very, very flexible like that.
Kevlar is so resistant to puncture, it's become synonymous with bulletproof vests and armour. It was originally invented in 1965 by chemist Stephanie Kwolek as a lightweight replacement for the steel bands in tyres.
Right, so this is very strong stuff made very thin.
Yeah.
Which means it's flexible. That's brilliant, Paul. The only
That's all
problem
it
is...
takes. That material is about 5 to 10 times as strong as steel.
Yep, just like carbon cloth, this miracle fibre is stronger than steel, between 5 and 10 times stronger. That's why they can afford to make it so thin.
So by making something like Kevlar thin, you can make it flexible and strong,
Yes.
but that won't
It's
hold
not much use, is it?
fuel, obviously, it'll
But
fall
the
out.
first thing we've got to do, we've got to turn that into some sort of fabric so that we can use the material to make a shape. But a fabric isn't going to hold the fuel in, is it? So we've got to encase that in something which is still flexible. So we take that and we combine it with the rubber encases it, and we get...
And this is the real deal. This is an actual F1
Yes.
tank. They've lent us this. It doesn't look much, but it's very, very clever. And also very expensive, thousands of pounds to make one of these. And that's combining then the properties of these two materials. So
Yeah.
this then is stiff and strong, and it'll hold the fuel without it running out.
Yeah. So basically, it's a rubber matrix reinforced with the Kevlar to give it the strength that you need.
Really, we should test this
I think we
with
should.
another flaming
Yeah.
arrow. I can't really...
No?
They'll be shouting.
Okay.
Very, very expensive. We've been lent it. We've got to give it back. However, I've devised something over here that might just do the job.
I have brought along the industrial cousin of the material used in the F1 tank, rubberized Kevlar.
This is the stuff. So this is the Kevlar fibre
Kevlar
inside.
reinforcement, yeah.
It's making it strong. And this is the rubber in it. And
Yeah,
it's still
nice and
flexible,
flexible.
but very, very strong, combining the properties of the two materials. Steve, have we got any more flaming arrows? I think we need another one.
Even though it visibly deforms the rubber, the arrow can't pierce the Kevlar. The bag is never punctured, the fuel never leaks, and the driver is safe.
It works. Okay, it was an unusual setup, but the principles are exactly the same. Those two materials working together can be flexible and strong. Most importantly, my fuel is safe in that rubber ball, because it's quite expensive.
The flexibility of the tank has an added benefit. It can be squashed to fit a tight space. And I get to enjoy the spectacle of two highly trained engineers using talcum powder to help post the crushed tank through the slot in the frame. The integrity of a stiff, strong frame would be ruined if you had to cut a big hole in it for your fuel tank.
If you need a hand at any time, just ask me. I'm here for the more technical bits, obviously.
So there you have it, F1's dirty little secret, talcum powder.
Easy.
Thanks to combat-proven body armour, F1 drivers know that the fuel just behind their head is going to stay in the right place. And the only punctures they have to worry about are in the tyres.
Tyres in F1 are not designed to last the full race distance. That means they have to be changed at least once during a race. How long does it take you to change a tyre? 15 minutes? 20? In the speed-obsessed world of F1, that wouldn't fly. Formula One mechanics can change all four wheels in less than 10 seconds. The key is having a pit stop crew drill with military precision and the right tools. Instead of 4 or 5 fiddly bolts, F1 wheels have one massive centre locking hub, which can be spun off with an air gun in less than a second.
Looking at and listening to an F1 car, you might think that only serious rocket scientists and design engineer types have anything to do with actually making one. But we must not forget the vital role played by prehistoric blacksmiths, because the technique used to make this sword also helps an F1 car flash around the track.
Things that go fast tend to get hot. F1 cars are no different. Some of the hottest and most stressed parts on an F1 car are the wheels. They can rotate 150,000 times in a race and encase brakes that can work at temperatures of 1,000 degrees Celsius. Road cars use wheels made of steel. No good for F1. It's too heavy and too weak. So, what's the alternative?
The material they use is this, magnesium, which has many useful properties. It's also used in this that I have in my hand, which is, well, it's a fire-starting kit, which is a worry. And just in case you didn't believe me about this particular property of magnesium, I thought it better to come away from the expensive F1 car to demonstrate. First, scrape some magnesium off. Next, hit it with a spark off here. One of those. And you really want that in the wheels of your F1 car.
In rare circumstances, such as when a puncture allows the wheel to scrape along the ground, magnesium rims can catch fire with dramatic effects. So why does anyone use magnesium to make wheels for racing cars? Same again, magnesium is strong and light. On F1 cars, lightweight strength wins over the small risk of fire, and it's one that's worth taking. Magnesium is up to the stresses of rapid acceleration, high-speed cornering and braking. But to make it even stronger, the F1 engineers borrowed an ancient technique for manipulating metal. If you want to shape metal, you can just cast it, melt it and pour it into a mould, as modern smiths Mike Rosser and Craig Jones show me.
It will still be extremely hot.
I can't undo it. I'm not manly enough. No, it's a test. I can't undo that. How?
All right, I'm not actually a blacksmith, clearly. Look at that! And that's what we just made.
One mallet. There we go.
And we just made that mallet. And it's not just simple things like hammers that can be made by casting either. More ornate objects like my sword here. See, that's cast iron. Really quite delicate and quite clever. Again, made by casting. Ah! Oh, Lord, I have dropped my sword. And, yeah, I think what I've done there is demonstrate perhaps a weakness. Some things are best made by processes other than casting. Fortunately, they can do that here as well. Chaps, broke my sword.
Yeah, fortunately for clumsy swordsmen and F1 wheels, there is another process which leads to a far stronger end product. The ancient technique of forging.
Hit it, basically.
Hit it basically, if we work in the edges.
Forging is the shaping of metal using localized compressive forces, or smacking lumps of metal repeatedly with a big hammer.
So this is forging.
Yep.
Forging most metal aligns its internal grains, which makes it naturally strong.
You'll need to put it back in the fire now and get some more heat into it.
By contrast, in cast metal, the grains are randomly distributed, creating points of potential weakness.
I'll tell you what, while nobody's looking, do you want to straighten it for me? Just straighten it up, and then we'll cut this bit out.
After many, many back-breaking, arm-wrenching hours at the forge, my blood, sweat and tears pay off.
Oh, yeah. That's just about perfect. I did that. All of that. Obviously, normally it would take somebody a long time to learn how to do this. Can you go and finish mine off for me?
I'll go and have a look.
Yeah.
With a little gentle buffing from my glamorous assistant, my sword reaches showroom condition.
Thank you very much, thank you. And straight away, my forged sword already looks a lot better than my cast one. It's lighter. Is it stronger? Yeah, clearly. That's a lot stronger than my cast one.
That's why F1 teams use forged magnesium wheels.
Forging is better than casting. And that's before we even consider the weight, because this whole sword, the forged one, weighs less than just this shattered portion of my cast one.
And the same is true for wheels. A forged wheel will be lighter and stronger than a cast one. As you'd expect, F1 teams have armies of blacksmiths turning out wheels. But not really. The process is somewhat more industrialized. A semi-molten alloy is crushed into shape using a force of 9,000 tons. The grains are aligned, and you're left with some incredibly strong wheels. Just pray you don't get a puncture.
Everything about an F1 car is designed to get it from the grid line to the checkered flag as quickly as possible. And it's a spellbinder for millions of people all around the globe. But a huge chunk of that racing doesn't take place out there on the track, because the engineers compete constantly and with incredible ferocity to gain just a few milliseconds advantage over their competitors.
And that means being on the very cutting edge of science and engineering, discovering technologies which end up far from the race circuit, almost as far as Mars, in fact. Usually, technology trickles down from space exploration. Formula One cars turn that on its head. Yes, the high-tech plastics that went into the Beagle 2 Mars lander came thanks to Formula One cars.
And at the risk of overstretching the metaphor, they are like butterflies, say, even in death considered objects of beauty and prized by collectors. And it is easy to be seduced by the stark, functional beauty of these things, by the depth of craftsmanship. But it is worth remembering they owe their very existence to some surprising engineering connections.
The first truly accurate cannon. The very first wing. A jet engine.
So any second now, it's about to snap.
Oh yeah, there it goes there, look, look. Body armor. And a blacksmith's forge.
I look menacing, I know.